some technical troubles we have been having last time about the commutation algebra of SO31. So, let me write down the algebra first, because that is the most crucial thing to worry about. So, our problems arose because we used a slightly unusual convention, and basically what we adopted was what you would call Hermitian convention, and this is non-standard. In quantum field theory, and the other one is a mixed one, Hermitian and anti-Hermitian. So, let me here quote Jackson, because that is a standard textbook, and even if I have made various errors of sign, I don't think there will be errors there. So, Jackson's convention is that with everything real, Si Sj equal to epsilon, everything is real here, so there are no i's at all, okay. And therefore it is automatically, so it is, yeah, I'm sorry, so I have to correct this. So first there is Jackson has this, which is all real and therefore actually not Hermitian. So the rotation matrices are antisymmetric, okay, and so he uses S transpose equal to minus S. That is how his rotation matrices are, and so he has Sk, and then Sj, Sikj are epsilon ijk kk, and ki kj equal to minus sign epsilon ijk sk. Now to recover our notation from this, which was Hermitian, we need to do the following. We defined J to be equal to I times S. Okay. Basically this is what we did. This makes everything Hermitian because the k's are symmetric. They were just 1 minus 1 in the zeroth row and column, and the rotation matrices were antisymmetric, but now if you multiply by I, then they become Hermitian. So this whole notation becomes Hermitian, and in this case I get so it requires you to put supply i's everywhere. This we can see because I put a minus sign on the left side here and split that minus sign as I and I, so it will convert both of these into j. But now I have a minus sign here, I split it into again I and I, leave one I in front and other I is absorbed by this to become j. In the next line I supply only an I. First line I supply a minus sign, second line I supply an I times S will become j, and here no change except that the I will sit in front. And finally in the last line I supply nothing, but I split the minus sign into I and I, and put one I into S. So it will just become equal to Ki Kj equal to I epsilon Ijk Sk. Okay. Now if I did this, I got into trouble. So after this, if I do J plus Ik, J minus Ik, it doesn't work. But the thing that does work is the mixed Hermitian and anti-Hermitian formalism followed in quantum field theory literature. Yes. What did I write? Oh, I have to write J. In the mixed Hermitian anti-Hermitian formalism, K's are actually anti-Hermitian. So we will not try to write any matrix representation, but I will just say that in this case, the J are Hermitian, but K are anti-Hermitian. And this you can find in Weinberg Quantum Field Theory Volume 1. Okay. In this case, the commutation relations are the way I flipped the sign suddenly last time, but you can be sure that if you use this convention, then you get this algebra. Ji Jj equal to I epsilon Ijk Jk, and Jk. So let us remember that we will always write, in order to not get lost, rotation produces a rotation, and then act with rotation on a boost that produces a boost. So that is the second line here. Jk produces I epsilon Ijk Kk. But the third line, which is Kk, or that is Ki Kj, in this case turns out to be equal to minus I epsilon Ijk Jk. Two boosts leads to a rotation, but with a minus sign. I believe that you can get this and this mixed Hermitian anti-Hermitian notation if you multiply also the K by an I. Okay. So J as here, J equal to I times Jackson's S. Jackson uses everything real, so at least that is very simple to follow. And the real matrices are multiplied out with nothing left to imagination, so you can check everything. But also make the K nu here I times K of left side. Okay. So if you do this, then because the K were just 0, 1, 1, 0, 1, 1 type of things, if you multiply by an overall I, they become anti-Hermitian. They were symmetric to begin with, so they become anti-Hermitian. So that then tallies with this, and I think this is the algebra you will get. And that you can also quickly see if you supply I here. So supply an overall minus sign, that will make it I and I, and then put the minus sign here, which will remove this minus sign. But then you need to put an I to make this into J, which will require you to put minus I in front. Okay. So this and this tally, and this is what this is the notation we will follow. So in this notation, we then introduce well, I just want to rely on my general argument that if you have rotation in a plane and in another plane, if the planes don't share any axes, then these rotations are independent, they will commute. But if they share one axis, then that common axis goes away and you get a rotation in the only the third direction. So if you do x, y, y, z, then the y drops out and you get an xz rotation. So if you have 0, 1, 0, 2, which are two boosts, then you get a 1, 2 rotation. How to imagine it probably requires you to, firstly you can do it with SON instead of SO31 and then try to, but that is the simplest way to think about it, and that you can check algebraically by doing this or by taking some object and doing infinitesimal rotations, xz rotation, zy rotation will leave behind an xy rotation. That's what the commutation does. Okay. In the mixed notation, which is what we will stick to because it is standard in quantum field theory, we now introduce this AI equal to 1/2 Ji plus Iki. Now this gets a little confusing in some sense, but let me just first write it and introduce Bi to be equal to 1/2 times Ji times minus Ki. We note that this way then the A and B are Hermitian because K is anti-Hermitian but multiplied by an I and J is Hermitian to begin with. Now if you work out that the AI will produce I epsilon ijk ak, and we did this last time, except that the only thing was last time I was writing kj commutator and not jk commutator, so there is a sign change, but otherwise it's the same. Okay. So this we have checked last time, provided we adopted this convention, defining A to be j plus ik, and then I suddenly switch to writing this algebra, so then it works out correctly. Okay, so you can check this, and similarly that the B's do the same thing. And the most beautiful part of it is that they mutually don't interfere. A with B is 0. Okay. So as a result, the SO31 is equivalent to SU2 cross SU2 but with complexification. So as algebras, okay. So you can see what has happened. The J is equal to I times the real rotations S of Jackson. So this is imaginary. The K was I times the real K's, but we put I times that. So we retain essentially a real piece here and a complex imaginary piece here. So this is intrinsically a complex algebra created, and that is when it resembles this SU2 algebra. So it is a sort of a pseudo trick. It's not real in isomorphism in the full group sense, but certainly as algebras they are isomorphic, it looks the same. Once it looks the same, we can deploy all the tricks that we use for finding the representations of this, which is, as you know, the raising and lowering operators. SO31 in the form JA comma JB, where A vector square will be equal to JA into JA plus 1 and B vector square will be JB into JB plus 1, etc. Because each one just became A and B individually is like resembles an SU2 algebra. So this raising lowering trick will work, and you can apply the same arguments and you will find representations that go from minus J to plus J. So with vectors, now from the point of view of physics, the representation, although it is classified by this, what really we observe, we can, for any massive particle, we can always go to its rest frame. We can boost ourselves into its rest frame. So for massive particles, we only need to worry about its rotations. So physical application. In the rest frame of the particle, in which case it will be the J really, which happens to be equal to A plus B, right, because we defined A and B like this. So if you add, then you get A plus B, then you get J back. So J is equal to A plus B is sufficient to classify the representations. To list the representation vectors. So rotations alone are enough to give you the required basis vectors, and then you can find the wave function in any other frame of reference simply by boosting, by applying a boost which will be exponential of this A plus B. So and here is where the mischief enters. You can write theta A or theta I J I and plus I, I'm sorry, U equal to exponent I times first let us write theta A I A I right plus I theta B I times B I, or call this something else. We have been writing, so call it J and put this K. So we have 6 parameters, theta A 1 2 3, theta B 1 2 3, J and K equal to 1 2 3, and boost means boost K happens to be equal to A minus B divided by I. So if you want pure boost, then you adjust you want A minus B. So theta B is equal to minus of theta A J. You choose the parameters to exactly equal, then you will be carrying out a boost. So that is one thing. The two important comments now are that one is about, I hope I don't forget telling them, one is about non-hermiticity of this, the other is more importantly that, so properties of such reps, one is that we do want space inversion to be part of our symmetries. If you want space inversion to be part of our symmetries, then we can see that under space inversion, J goes to itself. J is a pseudo vector, remember? So it is like xy rotation. But if you flip sign of both x and y, then it will not change. So space inversion means that x go to minus x. Then J goes to J, sometimes because it's called pseudo vector. Or note that Jxy will remain Jxy under both x and y changing signs. If you flip both the planes, then it remains the same, both the axes. But k will go to minus k because it is a space-time boost, and time axis you are not changing. So only the space axis, space part changes, and what this means is that you are forced to take JA equal to JB. So if you want this to happen, under this A and B get exchanged, right? Because A is J plus K, B is J minus IK, I doesn't even matter. The point is that J parts remain same, but K parts change sign. So under space inversion, A and B get exchanged. Thus, any realistic particle, massive particles where we can demand this, well, actually we need not say. So, all particles that obey space inversion must have Ja equal to Jb. The highest weight has to be same, right, because otherwise the representation will remain imbalanced. Where had we written some kind of JAJB? Yeah, this thing. A representation like JAJB, where one of them runs over, let's say, -5 to +5, but other one only -3 to +3. Under space flip, they will get exchanged. So that cannot happen unless JA is equal to JB. So you are forced to have JA equal to JB. Here the interesting historical fact is that the neutrino in 1956 was realized to be purely left-handed and completely massless. So for massless particle, actually you can get away with using only JA or only JB and not the other one. Thought to be massless. In 1956, weak interactions were found to be involve only left chiral neutrinos. Or right chiral antineutrinos. So you could only use either JA or JB description without invoking both, because you didn't need the sum J there. You didn't have this requirement of A and B getting exchanged, and it was sufficient to use JA comma JB equal to 1/2 0 representation of the group. Firstly, the two didn't need to be equal, and one of them you just set 0. One of them is enough because there are only two spin states, either rotating so it's spin and momentum gets correlated. If it is going this way, then it has to be counterclockwise. It is coming towards you, then it has to be clockwise. So either it's going away from you or towards you, and there are only two spin states. You cannot have anti-neutrino going being left chiral. So it was sufficient to use this. This has now changed as of year 2000 or so. We now know that neutrinos have a tiny little mass. So this description is still mostly valid, but the chances are that there is the other half present, 0 plus half, and also the possibility that the neutrino is quote a Majorana particle, which is a real representation. So I hope to do it separately, but this is just to say that when you impose parity, then A, B get exchanged and you are forced to have J equal to JB. But if there is no parity, if there is actually for some reason in nature parity violation, which was a huge shock to everyone, that weak interactions had no right-handed neutrinos, no right chiral, and which is true till date. At least the weak forces do not see the right chiral neutrinos. We do see slight mass to the neutrino, which probably means there is a right-handed component, but that right-handed component does not enter the weak force. That much is certainly true. So it was sufficient to use this, and the theory was has only CP invariance but no individual P separately. So if you perform a P transformation, you will get a right chiral neutrino, but then you should do a charge conjugation as well and make it into antineutrino, then the physics would be fine. That is what is observed in nature. So it was claimed that this is still true. Till date it is true, although the neutrinos are massive. The weak interactions are only CP invariant and not P or C invariant. Now the other comment, so one was about this. The other is about, I said properties somewhere, right? Yes. So one property is this. The second property is also interesting, is that we only get the representations are not unitary. Which are finite dimensional. Are not unitary because the group is pseudo SU2 cross SU2. If you had a strictly compact group SU2, then it would have been, the representations would be finite dimensional and unitary, like we proved in the using Schur's lemma. But in this case, exponential I times theta A, let me write this notation, theta A dot J A plus I theta B dot J B dot B, which can go into something equivalently into I times some theta dot J and minus omega dot K, right? That is what it would become, because if we put A equal to, so let us just take a look. So if we put A equal to J plus, so there is no I here. So A will have J plus I K. So that I times this I will make it only K. So there will be no I here. It will be like this, with theta and omega both real, okay, but K anti-Hermitian. So here, okay, let us work out. So if we have theta AI times Ji plus IKI plus theta Bi into Ji minus IKI, then we get theta AI plus theta Bi times Ji and plus I times theta AI minus theta Bi times Ki. So, if you had boosted with I in front, then this I will drop out and this will be a real parameter. Theta and omega are real parameters. But this is an anti-Hermitian operator. So, what we find is that this is no longer a unitary matrix actually, and that is why you will not get, so it is not actually unitary, the pseudo unitary, and k dagger equal to k minus k. So, the representations are finite dimensional but intrinsically complex. Now, why this was important was because the complexity of description of electron having to, so you remember the Pauli matrices are intrinsically complex. You can have 1 1 1 minus 1, but you have to have minus I. You cannot escape the complexification of the representation because of the fact ultimately that it has to do with the Lorentz group, and you are trying to get a finite dimensional representation of a otherwise non-compact group. So, this is no surprise because actually accords with non-compact nature of SO31, right, because the boosts are not compact. You can have you can boost arbitrarily close to speed of light, but you cannot actually hit the speed of light. So, it remains a non-compact. The boosts are form non-compact one parameter subgroups.